Hello all. Welcome back to the lecture series on analog communications, module 5. Currently, we are discussing about figure of merit calculations in continuous wave modulation schemes. In the previous lectures, we have derived for double sideband suppressor carrier EAM, and we have also estimated for double sideband full carrier EAM. For DSB-SC, figure of merit is a unity. Whereas for DSB-FC, figure of merit is less than unity. In continuation of the discussion, let us proceed for the figure of merit for a single sideband suppressor carrier EAM. The first and foremost step in deriving the same is draw the receiver model. Draw the receiver model. For what? Receiver model for SSB, because you are deriving for single sideband modulation, right? So we have to draw the SSB receiver model. So how it will be? So in DSB-SC, we have used coherent detection. In SSB-SC, we are also going to use the same detection, that is coherent detection. In coherent detection, the incoming signal is going to multiply with a locally generated carrier signal, which is same as the transmitted carrier signal. For this purpose, we are going to make use of a product modulator where we multiply. Then we are going to take the help of a local oscillator. This local oscillator will generate the carrier signal cos omega CT, whose output is passed through a low pass filter. The output will be represented as Y of t. Output of part modulator, let it be V of t, and output of the IF section will be X of t. This is the first step in deriving for the SSB, SSC, AM figure of merit. Then step number 2, estimate. These steps are common. Estimate input signal power, SI. We are representing as SI. Okay. So what is the expression for SI? SI equals to 1 over 2 pi, 0 to 2 pi, S square of t dt. What is S of t? Modulated signal. In this case, S of t is the SSB signal. If we are assuming LSB transmitted, you can consider USB also. Assuming lower sideband transmitted, the expression for the S of t can be given as AC by 2 M of t cos omega CT plus AC by 2 M cap of t, which is nothing but the Hilbert transform of the message signal. M of t is the message signal, M cap of t is the Hilbert transform of the message signal. This is obtained by passing the message through a filter whose transfer function is minus j into sigma of f. Okay, so input signal power SI equals to 1 over 2 pi, 0 to 2 pi, first term, AC by 2 M of t cos omega CT whole square dt, right? Plus second term, 1 over 2 pi, 0 to 2 pi, AC by 2 M cap of t sin omega CT whole square dt. This is from standard notation. If the mathematical expression is available in time domain, average power is the mean square value. So it will be equals to, I will take common, that is AC square by 4, okay, 1 over 2 pi, 0 to 2 pi, M square of t, cos omega CT square means cos square omega CT. It can be represented as cos 2 omega ct by 2 dt, first term. Similarly, second term, AC square by 4 into 1 over 2 pi 0 to 2 pi m cap square of t into 1 minus cos 2 omega ct by 2 dt. As m cap of t is the Hilbert transform obtained by passing the message signal through minus a filter of transfer function minus j signum of f, the magnitude square will automatically equal to same as the m of t power. The power of the m of t, the power of the m cap of t will be same. So it will be equals to AC square by 8p first term. Similarly, AC square by 8 into p second term, which gives you the total power as AC square p by 4. This is the input signal power. If we go in other way, what about cos 2 omega ct? And what about minus cos 2 omega ct? The integration of those terms will automatically 0. That is the input signal power. Now, step number 3, we are going stepwise. Know what is the input noise power? We have told in the previous lectures, the input noise power always estimated over the message bandwidth. That is from minus W to plus W. So N0 by 2 is a constant taken outside minus W2 plus W dF. That is equals to N0 by 2 into 2W. So input noise power will be equals to Wn0. Now we want to estimate the signal to noise ratio at the channel output. That is equals to Si by Ni. So AC square P by 4 W N0. This is the input signal to noise ratio. Now we have to estimate the output SNR for calculating the final figure of merit. So this will be obtained by first writing the expression for x of t. What is x of t? Output of the IF section, which can be represented as S of t plus N of t. What is N of t? Narrowband noise. Let us carefully observe the difference in analysis between the previous case and this case. Right? So the SSB signal with the lower sideband transmitted is represented as AC by 2 m of t cos omega ct plus AC by 2 m cap of t sin omega ct, where m cap of t is the Hilbert transform plus, see the difference here, the narrowband noise component is going to change from the previous discussions. Here we will have 2 pi into, instead of Fc, we will be having 2 pi into Fc minus W by 2t. Make a note. Minus Ns of t, the quadrature component, into sine 2 pi Fc minus W by 2t. Yeah. In the previous case, Nc of t cos 2 pi Fct minus Ns of t sin 2 pi Fct. But in this case, as the center frequency is Fc minus W by 2, like this, you can have a glance here. This is your transfer function of the IF section. You are transmitting only LSB, Fc to Fc minus W, minus Fc2 minus Fc plus W. So center frequency is how much? Center frequency will be Fc minus W by 2. This must be carefully remembered. Clear? Previous case, cos 2 pi Fct, sin 2 pi Fct. In this case, as the center frequency is differing, you are multiplying with cos 2 pi Fc minus W by 2 t. Now, this is multiplied with a locally generated carrier cos 2 pi FCT or cos omega CT, whatever the term, you can represent in any way. So AC by 2 m of t cos 2 pi FCT, cos 2 pi FCT, cos square 2 pi FCT plus AC by 2 m cap of t, okay, cos 2 pi FCT into sin 2 pi FCT. This is corresponding to the message components. What about other things? Plus NC of t into cos 2 pi FC t into cos of 2 pi into FC minus W by 2t. First term minus NS of t into cos 2 pi FCT into, yeah, sin 2 pi FC minus W by 2t. Cos A, cos B, first term, sin A, cos A, sin B, second term. Let us simplify further. Equals to AC by 2 into m of t into 1 plus cos 4 pi FCT by 2. Take a care. Or you can write cos 2 omega CT also, no problem. Cos square theta equals to 1 plus cos 2 theta by 2. So 2 into 2, 4, no? So right. Similarly, AC by 2 into m cap of t into 2 sin theta cos theta sin 4 pi FCT, right? Plus here NC of t into cos A plus B. Come on, cos A plus B, 2 pi FC, 2 pi FCT. So, okay, cos of 4 pi FC plus W by 2, cos A plus B. Okay, this will be minus, of course, T. We are multiplying with how much? This will be cos 4 pi FC. Wait a minute. We have to consider the component corresponding to, let me erase this term. Okay. Right. Okay. Cos 2 pi FC, 2 pi FC, 4 pi FC, then 2 pi into W by 2. So automatically it will be minus pi WT. This is A plus B plus cos A minus B, 2 pi FC minus 2 pi FC. Okay. Cos pi WT, this is NC of t plus NS of t into, what is second term we have here? See, cos A sin B, this is minus, cos A sin B equals to sin A plus B minus, okay, sin of 4 pi FC minus pi WT minus sin pi WT. Okay. So these terms are passed through a low pass filter. So after low pass filter, what you are going to consisting of? The output of the low pass filter will be consisting of y of t equals to, let us go term by term. First term, AC by 4 into m of t. Okay. Second term is first term, this cos 4 pi FC is removed. And similarly, second term is completely removed, sin 4 pi FCT. Okay. Plus NC of t by 2 cos pi WT plus NS of t by 2 into sin pi WT. How by 2 came? 2 cos A, cos B, no. So this is by 2, this is by 2. Here there is no 2, na? That's it. So these are the components present at the output of the low pass filter, which contains message component AC by 4 into m of t, which contains the noise component NC of t by 2 cos pi WT plus NS of t sin pi WT. So let us estimate the noise power, output signal power SO. Let me denote. That is equals to 1 over 2 pi 0 to 2 pi AC into m of t by 4 whole square dt. This will be equals to AC square by 16 into P. What is P? P is the power of the message signal. 1 over 2 pi, 0 to 2 pi, m square of t dt. Clear? Now, let us estimate the output noise power NO. Last step in the complete discussion. Okay? Just we are going to we are discussing all these things about using steps. No, so S3 completed. This is step number 4. SO completed, and now step number 5. NO. What is the output noise power? So what it is consisting of? NC of t cos pi WT plus NS of t sin NS of t by 2 into sin pi WT. Okay. So now what we have to do? We have to take these components. The output noise power will be NO, that can be given as 1 over 2 pi, 0 to 2 pi. We have two terms, right? NC of t cos pi W by 2 whole square dt plus second one 1 over 2 pi 0 to 2 pi ns of t by 2 sin pi W t whole square dt. Then if I simplify further, this is equals to 1 by 4, okay, 1 over 2 pi, 0 to 2 pi, nc square of t cos square pi WT dt plus 1 by 4, 1 over 2 pi, 0 to 2 pi, ns square of t sin square pi WT dt. Again, cos square theta equals to 1 plus cos 2 theta by 2. Sin square theta equals to 1 minus cos 2 theta by 2. So, this can be further represented as 1 over 2 pi, 1 by 8, 0 to 2 pi, nc square of t dt plus 1 by 8, 0 to 2 pi, ns square of t dt. Why? Because the other terms, that is cos 2 pi WT term will be 0 under the integral from 0 to 2 pi. However, as we cannot have the mathematical expression for in-phase component, this can be simply mentioned as SNC of F dF plus 1 by 8 minus infinity to infinity SNS of F dF. Okay, where SNC of F is the in-phase component or in-phase components PSD, while SNS of F is the power spectral density of the quadrature component of narrowband noise. Of narrowband noise, it must be remembered. The term N corresponds to noise. SNC of F, power spectral density of in-phase component of narrowband noise. SNS of F, power spectral density of quadrature component of the narrowband noise. Now, how they are obtained? Yeah, there is difference. N SNC of F equals to earlier Sn of F minus Fc plus Sn of F plus Fc. But now, for SSB, SNC of F will be equals to Sn of F minus Fc minus W by 2, because center frequency is changing. Na? plus Sn of f plus fc minus w by 2. This is the difference one must remember carefully. Okay, so with this in mind, let us estimate. First of all, narrowband noise. Sn of f. How it will be? Okay, fc minus w. This is fc minus w by 2. Similarly, LSB is transmitted na minus fc plus w, and this is minus fc plus w by 2. This is 0. Now, this should be shifted to the right or shifted to the left by an amount fc minus w by 2. Suppose I want to shift right. So what I have to do? Add fc minus w by 2 everywhere. Clear? I want to shift left. Subtract fc minus w by 2 everywhere. So what is the magnitude here? The magnitude is n naught by 2 known for us. Then, okay, this is SNC of f. How it will be? Shift right. So add minus w by 2 plus w by 2. And again, we have one more component here centered at 2fc. This will be removed. Similarly, this is Sn of f minus fc. Similarly, Sn of f plus fc. Shift left. W by 2 minus W by 2. Magnitude is N naught by 2. Previously also the same. Here, one more component at minus 2fc centered around. Okay. So this is also getting cancelled. If you add both, SNC of f will be equal to, from the limits, minus W by 2 to W by 2. This is N naught. How N naught? N naught by 2 plus N naught by 2 is N naught. Okay. So, similarly, we can derive for Sns of f can also be derived, which is same as Sns of f equal to Snc of f. So, thus, minus W by 2 plus W by 2 f, this is N naught, and this is equals to Snc of f as well as Sns of f also. Now we want the power, right? Ultimately, why are you doing all these things? 1 over 8. Yeah. How, where to where? Minus W by 2 to W by 2. N naught df plus 1 over 8 minus W by 2 to W by 2. N naught df. So what this will be? W n naught by 8 plus W n naught by 8. Why? Because integration of 1 is f W by 2 minus of minus W by 2 is W. So, which gives you W n naught by 4. This is the output noise power. Previously, we have estimated the input signal power, input noise power. It is with you, right? Where is the expression here? Have a glance one more time. AC square P by 4W n naught. Now, we have to estimate the output signal power, output noise power. What is the output signal power? AC square P by 16. Okay. Now, let us just calculate the powers from the. So, the output signal to noise ratio can be obtained by dividing the output signal power with the output noise power. The output signal power is already estimated. We have the expression with us. So signal to noise ratio at the output equals to AC square P by 16 signal power by the output noise power. How much you got? We have got the output noise power as omega W N naught by 4. That is W N naught by 4. So thus it is equals to AC square P by 4 W N naught. So what is gamma? The figure of merit gamma equals to signal to noise ratio at the output divided by signal to noise ratio at the channel output. That is equals to AC square P by 4W N naught divided by AC square P by 4W N naught, which is equals to 1. That is gamma equals to 1 for SSB-SC also. In the previous case, DSB-SC-AM, double sideband suppressor carrier AM, also we got gamma value 1. In the case of SSB-SC, also we have got gamma value 1. So care must be taken in estimating the output noise power. Why? Because the center frequency of the IF section is different from the previous case, because we are transmitting only one sideband here. So thank you all. The next lecture, we derive the figure of merit for FM receivers. Thank you.